Okay, welcome back. We're going to do a little bit of thermodynamics today, so don't let the title throw you off. But we're going to approach it in a way that you're going to see us approaching things fairly frequently. We're kind of all about what's in it for us. So we're going to look at thermodynamics, but we're going to look at it, what are we going to use it for? What are we going to do with it? Then, after we do that, and light touch on that, I know you physical chemists are thinking, oh no, here we go again. So after a light touch on that, we're going to move into ATP, our biochem currency, and we're going to move into reactions and look at the kinds of reactions we're going to do. So I know you did thermo in general chemistry. I know you guys who have taken more chemistry courses feel like you have thermo coming out your ears. So, like I said, we'll do a light touch, but just a few things I want to remind you of before we get into it so that you can go through it pretty smoothly. So the system is really whatever we define it is, or define it as. Very often we're going to define the system as the cell, and the surroundings is everything else, everything that's not the system, basically. Don't forget that enthalpy is the heat content of the system, so a form of energy. Don't confuse that with temperature. Temperature is how hot or cold something is. Also, don't confuse it with entropy. Sounds really similar. That's the randomness or the disorder of the system. So we're going to talk about both the first law and the second law. What's different, though, than what you've done before is we're going to talk about it in the sense of what are we going to do with it? How does it apply to us? Where in general chemistry, very often, you just kind of say, well, here it is. Here's the first law. Here's the second law. And you're sitting there left thinking, well, yeah, so what do I do with that? So anyway, first law, as you know, there's a million different ways of saying it. The total energy of a system and its surroundings is constant. Energy can neither be created nor destroyed. And what we really mean by that is we're going to move energy. We're going to move it from the food that you eat to a constant available supply of energy for your cells. So we're going to turn calories into a molecule called ATP, and not literally turn it into, but it's almost a units game. The more calories in the food that you eat, the more ATP, that molecule that is kind of our currency, will get. We're also going to look at the second law. The total entropy of a system and its surroundings always increases for a spontaneous process. So we're going to look at what's that mean. We're also going to look at that word spontaneous a little bit. There's a few words that have a different meaning in chemistry than they do in everyday life. And it's a really good place to cause confusion with questions and everything if somebody happened to want to do that. Okay, so the first law is the law of conservation of energy, and I know you probably know that. The energy of the universe is constant. We can't make energy. We can't destroy energy. We can move it, transfer it from place to place. There's two ways to transfer energy, in the form of heat or in the form of work. So we're going to use that. We're going to move energy around. The second law is about entropy. If entropy is decreasing somewhere, it's increasing somewhere. And an example of that is, let's say we have two metal blocks and we put them together. One's hot, one's cold. They'll equilibrate. And equilibrium is a big part of this story. The hot one will get colder, the cold one will get warmer, and they'll both end up kind of lukewarm. Or if I have two lukewarm blocks and I put them together, they're going to stay that way. One's not going to get hot and the other one get cold. So we'll talk about this too and how this we kind of don't care about metal blocks, but how does this apply to our cells and what we're doing? So, a few quick examples, not super important, but just to kind of give you the idea. And we'll get into what's going on in our cells and everything with it. But I might have a container of oxygen and a container of hydrogen, separated, very nicely contained, very orderly. I pull the barrier out between my containers, or I dump them in together, and they all mix up. So I have higher entropy. Then give them a minute, allow them to react, they're going to get organized again. So rather than having a mishmash of hydrogen and oxygen, they get ordered. They become hydrogen peroxide. When they do that, though, and they get all orderly, as in their entropy decreases, or the system that contains them has a decrease in entropy, we send heat out into the surroundings. So we increase the entropy of the surroundings. Well, we're not going to be organizing hydrogen and oxygen and making hydrogen peroxide. But one place where we will see it very shortly, we're a couple of videos from it, is with proteins. We're going to talk about, we have just a bunch of amino acids. What happens to those? How do we organize them? Organize them into proteins. Organize those proteins into some kind of folded, organized structure. So it really will apply to what we're going to be doing. Okay, one of the first things we're going to spend a pretty decent amount of time on is Gibbs free energy. And I'm not quite sure what happened to this slide, but anyway, the part we care about in this is, where's Gibbs free energy coming from? And I don't mean literally where it's coming from, but we're going to use it. We're not going to calculate it. So by doing that, and you calculated it in general chemistry, so you've gone through that, that exercise. But sometimes when we use calculations that someone else has done, it makes us feel like we're pulling numbers out of thin air. We're not. And I don't want to give that implication. So I do want to back up for a second and talk about where the numbers are coming from. Excuse me, I'm sorry. So the change in Gibbs free energy of reaction is a function of several things. It's a function of the change in enthalpy of the system. It's a function of the temperature of the system. It's a function of the change in entropy of the system. So you could write the equation. And some of you guys have calculated it using this equation. So I would know this equation. And the common way to get asked this is Gibbs free energy of reaction, or delta G, is a function of all of the following except. So what you'll get given, I didn't mean to do that. What you'll get given is, you'll get delta H, you'll get T, you'll get delta S. So whatever is left after that, since it's an except question, is what you're going to be looking for there. So I would know this equation, and not just for the question, but I would know it because I don't want you feeling like we're pulling these numbers out of thin air. Okay, so what are we going to do with these numbers? We're not pulling them out of thin air. We're not calculating them, but like I said, we are going to approach a lot of things in the what's in it for us kind of realm. So what the Gibbs free energy is going to tell us is whether the reaction is going to go or not. It's a go or no go measurement. So let's back up for a second. Enzymes made our reaction go faster, go to the same amount of the same product, same equilibrium, same everything, other than you got there quicker. Delta G is telling you whether you're going or not going. It's simply a yes-no question. It's not telling you how you're going. It's not telling you how fast you're going. So that's going to get really important. I was going to say in a minute, but it's kind of important now too. So it's like, let's say you ask me, are you going to Orlando this afternoon? I can give you a yes or a no. That's it. I can't tell you how I'm going. Am I driving my car? Am I riding my bicycle? Am I going straight out I-4? Am I going by way of Atlanta? Whatever craziness. Yes, no, period. So that's delta G. Yes, no, and that's it. So what we're actually going to look at in delta G is the sign of delta G. So if delta G is negative, that's going to be our go. So negative delta G, that's a go. And we'll come back and talk about this in a minute. If delta G is positive, you positively have to put energy in to make that reaction go. If delta G equals 0, that's reversible. Well, what do we do with that? Does it go or not go? Well, remember Le Chatelier. So Le Chatelier said, if we have a system that's at equilibrium, it's staying at equilibrium. If it's not at equilibrium, it's going to equilibrium. So if delta G equals 0, it's a reversible reaction. It's at equilibrium, it has nowhere to go. If it's not at equilibrium, it's going to equilibrium. What's going to happen with our delta G equals 0 reactions is you're going to kind of forget about them. So what you're going to do is you're going to have your delta G's and negatives and your delta G's are positives. And you're going to be kind of digging around in those, and we'll talk about what I mean by that in a minute. And then you kind of lose the forest for the trees in a way. We'll focus so much, so strongly on those that you'll kind of stop and say, well, hang on, what do I do with this delta G equals 0? And I'll say, remember that whole equilibrium Le Chatelier thing? Usually at that point, you say, oh yeah, I forgot. Because you were so focused on the positives and negatives, and that's fine. So delta G is negative, the reaction's going to go. Delta G is positive, the reaction's not going to go unless you put energy in. But let's talk about a word that can get you in all kinds of trouble if you don't pay attention to it. And that word is spontaneous. So there's several words that have a different meaning in everyday language than they do in chemistry or biochemistry. So in everyday language, spontaneous has the implication of fast. If I said I made a spontaneous decision, you're going to take that as I made a quick decision without taking the time to do research. So in our everyday language, it implies quick, implies speed. In chemistry, no. In chemistry, all spontaneous means is that I have enough energy contained in those reactants for those reactants to become products, period. No anything, no information about how fast those reactants will become products. So be careful with that in questions. If you get a question about a spontaneous reaction, don't even think about speed, don't even think about enzymes. Just think, you're telling me in this question that I have enough energy contained in these reactants for those reactants to become products, period. I don't know how quickly they'll become products. I don't know anything about how they'll become products. I just know that they will. So all spontaneous means is that reaction is going to go. That's it. Nothing more than that. So be a little careful there. Okay, so delta G is negative, it's go. Delta G is positive, it's no-go unless we put energy in. Delta G is negative, that's a reversible reaction. And you know, in a reversible reaction, if it's at equilibrium, it has nowhere to go. If it's not at equilibrium, that's where it's going. So let's back up for a second. When we talked about enzymes, we talked about what they do. They increase the rate of reaction. We talked about how they do it. They lower the activation energy, or, saying the same thing again, they lower the energy of the transition state. A more general way of saying that is they make the path of reaction easier. Because they make the path of reaction easier, you do that path or travel that path faster. So they're all about the path of reaction. Remember back in general chemistry when you calculated delta G of reaction, you went to the back of your chemistry book and you looked up the free energy of the products, you looked up the free energy of the reactants, and you did products minus reactants. And I'm so surprised you're still looking it up in the back of a book. I did that in 1983. But anyway, you do. So you're doing products minus reactants. And when you did that, you were probably just hoping you got the right number and the right sign and the right units and not giving any thought to what it means. But think about it now, outside of sign, units, whatever. In this doing products minus reactants, I'm not talking about anything in between. I'm talking about my starting point. I'm talking about my destination. I'm not talking about how I got from my starting point to my destination. I'm not talking about the path of reaction. So what I'm really saying is delta G is independent of the path of reaction. So enzymes were all about the path of reaction. Enzymes were all about the path of reaction. Delta G is independent of the path of reaction. Be really, really careful with somebody trying to confuse you about that. And it's actually the reason we used to teach other things in between enzymes and Bioenergetics 1, but I moved it because I want these two topics back to back. And you're actually to get questions about both back to back. I completely lined that up because I want you to have the practice and handle it well and not have to worry about it after that. So delta G is independent of the path of reaction. Enzymes are all about the path of reaction. Delta G provides you no information about the rate of reaction. Enzymes increase the rate of reaction. So be careful with all of that. Really good place to try to confuse you if somebody was out to do that with questions. Okay, let's back up and do something else for a second. And I should have put a slide in here for room to write. So I'm just going to get rid of this stuff to give myself room because I forgot to do that. I usually line up my blank slides beforehand, but I missed a spot here. Okay, so let's talk about what we're going to do with delta G. We said if delta G is negative, the reaction's spontaneous. I have enough energy contained in those reactants for those reactants to become products. If delta G is positive, then I positively have to put energy in to make that reaction go. All right, well, great. Where do I get that? So let's say we have a process. I'm going to make up my little process here. I have A going to B, going to C, going to D. Guess that's all the room I have. Let's say A going to B, my delta G is, plus 10. B going to C, delta G is minus 20. Do a plus 5 here. And in a real reaction, we'll have some zeros in there and everything. But is this process going to go? And there's a couple things here. One is we're really, really good academically at focusing on one thing at a time. It's all our little one-track minds can handle. So I'm writing this out like I have one molecule of A going to one molecule of B to one molecule of C to one molecule of D. And that's the only thing I have going on in the cell, the tissue, the organism, whatever. And the truth is, I have all kinds of stuff going on all at once. We just kind of forget that and then have to bring ourselves back to reminding ourselves of that. So I have a whole bunch of A's going to a whole bunch of B's, a whole bunch of C's, not all at once, and have all of these things at once, A, B, C, and D in the cell all at once. So what I want to know is, can this little A going to B process happen? So the way I'm going to figure that out is I'm going to get my overall delta G. And what that is 10 plus minus 20 plus 5. And I'm going to add that up. Well, when I add up plus 10 minus 20 plus 5, I end up with a minus 5. So my overall delta G is a negative number. So since my overall delta G is negative, my little A to D process is going to go. And I'll say things like, this reaction will carry or drag along these two reactions. And what I really mean, if I were saying that more properly, less improperly, properly, what I would really mean is that I have enough extra energy in that B going to C reaction to give it to the A going to B and the C going to D reaction. The next thing that comes up, well, if A doesn't go to B, how can B go to C? Well, B going to C carries along the next A going to B. Because remember, we have all kinds of A's and all kinds of B's and all kinds of C's in the cell, not just one, even though our one-track mind's got to do step 1, step 2, step 3, and so on, because we think in a linear manner. And I know you guys say, well, we multitask. We don't have a one-track mind. No, you don't. You just switch tracks quicker. All right, so let's talk about where is this energy? How do we use it? Where do we find it? What do we do with it? So, a couple definitions first. And easy definitions, but I'm going to mention them a couple of times because I don't want you confusing them. We can have two kinds of reactions or two kinds of processes in terms of making or breaking molecules. We can have anabolic processes or reactions where we build up stuff. We might take little molecules and make big molecules. We might build up cells. But we're going from the little to the big is the point with anabolic. We can have catabolic reactions or processes where we take big molecules and break them into little molecules. It's a big catastrophe. We break stuff. So catabolic, big to little, anabolic, little to big. We can also categorize reactions and processes by whether they absorb or release energy. If they release energy, as in energy exits, they're exergonic, so energy exits. If energy enters, they're endergonic. So if they absorb energy, they're endergonic. Here's where you can get yourself in trouble. We can have catabolic reactions that are endergonic, catabolic reactions that are exergonic. We have catabolic reactions where delta G equals 0. Same thing with anabolic. So I'll hear you guys sometimes saying, well, catabolic reactions are exergonic and anabolic, whatever. Don't. Draw a line in the sand here and don't try cross-relating one to the other. So it can be catabolic or anabolic. It can be endergonic or exergonic. It can be reversible, so not endergonic or exergonic, and fall into either one of these categories. If you try mixing them and matching them, that's where you're going to get yourself messed up. All right, so we have a molecule, and we talked about it a little bit. That didn't work very well. Let's stick with this one. We talked about it a little bit in the context of DNA. So the molecule we're going to talk about is adenosine triphosphate. So what I have, I'm going to give you a copy of the PowerPoint. It's in your notes, so I hope it's in better shape. I have to make it fit the screen, so it moves stuff around on me sometimes. What I have is a ribose. I have an adenosine, or an adenine, I'm sorry. And when I put adenine and ribose together, I call them adenosine. So that's all great. That's not the business end of the molecule. I also have 3 phosphates attached. That's kind of the business end. So a couple things with this. One is we call ATP our biochem currency, our biochem money, whatever. But the part that does the work is the phosphate end. We abbreviate adenosine triphosphate as ATP. We're going to count and account for ATP. So ATP is going to be a big budgeting project. And what I mean by that is the same thing as any budget. In your personal budget, you look at how much money you bring in, how much money you spend, and you watch to make sure that you're bringing in more than you're spending. In your office, you're going to do that. You're going to look at, I'm making this much money, so I can only spend this much money, and make decisions like, well, I really want a new table this month. Can I or can't I? So we're going to look at ATP the same way. We're always going to be making ATP. We're always going to be breaking ATP. So it's always going to be an in and out kind of thing. Since we're going to be doing that following budgeting, whatever thing, we're going to pay a lot of attention to ATP. We are going to have molecules where this base might be something else. Might be a uracil, so it might be a UTP, might be a guanine, might be a GTP, and so on, CTP, whatever. So it might be these two things. We're going to keep track of those, and we're going to keep track of them in kind of a funny way. We're going to keep track of them in the sense that they work the same as an ATP, because the business end is the P part, the phosphates, but we're going to keep track of them as something different. If we don't recognize that although they work the same way, there's something different. It's like if I have a handful of Canadian money, it works the same way. It's money. Well, it kind of works the same way. It's not worth as much as US money, but I could spend it and I can make it and whatever, but I've got to recognize that it's different. That's my UTP, my GTP, my anything else TP. So be a little careful there. But the other thing is, with our TPs, well, 2 things. With any molecule that we tend to talk about it in abbreviations, and this is one of them, make sure you know the abbreviation and you know the real name. This one's usually pretty easy because we'll say ATP, and then you'll get a question that the answer is ATP, and you'll look, it's like, there's no ATP here, but then you'll look, oh, yeah, adenosine triphosphate is ATP, so you're all good. We have some other molecules that aren't quite as intuitive as that. So any molecule or anything that we talk about in abbreviations, make sure you're comfortable with both. But let's talk about the other end of it. So what we're going to do is when we want energy, we're going to break this bond between two phosphates. So what I'm going to do is I'm going to break that high energy phosphate bond. So what I'll do is I'll take the phosphate off. I'm just going to use a P for that, and I'll get this energy. So I can use that energy then to go drive a reaction or do whatever I need to do with it. I might use the phosphate or I might not. But when I do that, I'm left with adenosine diphosphate, ADP. Then I might, not very often, and we'll talk about that in a minute, then I might break this bond, break the other high energy phosphate bond. I'll get the phosphate. Again, I'm just going to use a P. I might use it or I might not, but I am going to get and use the energy. Now I'm going to be left with AMP, adenosine monophosphate. So let's say I've done that. Then I'm going to go and eat something. I'm going to go eat my, peanut butter Oreos. And my peanut butter Oreos have, how many calories. Let's say 100 calories per Oreo. I have no idea. I'm making that up. So what I'm going to do, though, is I'm going to take those calories. I'm going to go through all my steps, all my stuff, all my processes that we'll be doing in Try 2. And I'll eventually take those calories, replace this energy, put a phosphate back on. To put a phosphate on, I need two things. I need the phosphate, but I also need this energy. Then I might need to eat another Oreo. Take those calories, replace this energy, find another phosphate, and put it on, and go back to ATP again. I'm always going to be going back and forth doing that, going most often from ATP to ADP, and then ADP back to ATP. Better picture what we were drawing with me just taking a phosphate off. Take one off, I'm left with two phosphates. ADP, take all three off, take one off, I'm left with two. Adenosine diphosphate. Take two off, I'm left with one. Adenosine monophosphate. Okay, let's talk about something. I just said most often we're going to go from ATP to ADP and back to AMP. We're going to do that because it's actually more efficient to do that. So I'm going to go from ATP to ADP. I could go from ADP to AMP, and there's actually only one place that we're going to do that. Here's the reason. The ATP to ADP step is more efficient. So it's more efficient for me to go from try to die and then die back to try. And a way of looking at this is, let's turn energy into money. Let's say going from ATP to ADP, I get $10. Going from ADP to AMP, I only get $5. My proportion is roughly correct. My units obviously aren't. And I use money analogies a lot. And let me talk about that before we go any further with it. I know a lot of you are going to really, really hate it. And that's okay. The reason I use the money analogies is we all have to think in money to manage our everyday lives. You think about how much money you spend versus how much money you make and how much money you can spend based on how much money you have and stuff like that. It's just part of managing our everyday lives. I'm not implying you're all about money. I'm not implying you're entering this profession for money. I'm just using the fact that most people think in terms of money. I've found over the years, if I say you make this many molecules and use this many and all that, it takes you longer to click into that than if I say you make $5 and it costs you $2 to make it, what do you have left? You'll instantly say $3. So anyway, I'm just using that learned ability that you've developed over the years. That's it. All right, so if going from ATP to ADP gives me $10. I'd rather do that than go from ADP to AMP. It's only going to give me 5. So that's what I do. So I'll do this over and over because it's more efficient. So I'd rather, say, take 2 ATPs and go to 2 ADPs, because that's going to give me $20, as opposed to going from ATP to AMP, I'm only going to get 15. So in our reactions, in our stuff, we're going to see this going on, or ATP going to ADP, over and over to drive our reactions. Then we're going to go back and say, well, I ate my Oreos or whatever. I'll take my ADP back to ATP. Then I'll go and do my stuff. ATP to ADP. Then I'll eat my Oreos, and so on. So we're going to be going back and forth here most of the time. There's one instance, I think, just looking ahead, that we're going to go down to AMP. So even though we're talking about doing both now, we're really going to stay on one end of that. Okay, and the real numbers, like I said, with my dollars, I was roughly proportional, but we think better that way, typically. Okay, so let's talk for a second about this delta G thing before we leave it. So we said delta G is negative for spontaneous reaction. Again, spontaneous is telling me nothing about time. Delta G is positive for a non-spontaneous reaction, or delta G is positive means I positively have to put energy in to make that reaction go. Again, remembering that spontaneity tells you nothing about speed, nothing about rate of reaction. This is just a go or a no-go measurement, and it's not telling you how you go, how fast you go, or anything. But let's also talk about the numbers. Again, we're not going to calculate any. You've done that, been there, done that. We're going to use the numbers that somebody else calculated. But here's the thing with those numbers. When you did those calculations in general chemistry way back when, you were calculating the numbers under ideal perfect conditions. Here's the thing though. You're not ideal nor perfect conditions. Your cells are not running under ideal perfect conditions. So this is kind of like, let's say you just bought a brand new car and the sticker on the window says you're going to get 30 miles to the gallon. Would you risk, if you were to drive 30.0 miles, do you think you're going to do that if you just put 1.000 gallons of gas in the tank? You don't know. That number was calculated under ideal conditions, probably downhill with a tailwind on a icy road, I don't know. But real life is not ideal. So no, I'm probably going to drive 28 miles on that 1 gallon or whatever. So when we say that our delta G is negative and it's going to give us, it's minus 20 kilojoules per mole or whatever, meaning based on that, it's going to give us, 20 kilojoules per mole, it's not. That's under ideal perfect conditions. Since you're not ideal perfect conditions, you're not getting that. Or if delta G is positive and says you need 18 kilojoules per mole, you're not going to make it on 18. You probably need 20. So kind of like the gas mileage thing, these are ideal theoretical numbers. So if our overall delta G just hits 0, that's like you trying to drive that 30 miles on 1.000 gallons of gas. Probably not going to happen. We always need a buffer, a margin of error in there. Okay, so like we said, we're always making ATP, we're always breaking ATP. It's going to be like your office. You're always making money, you're always spending money. So we have a turnover in there. When we get going, we're going to talk about making ATP. We're going to talk about quick ways of making ATP. We'll talk about creatine phosphate in the muscles. That's a quick source of ATP. We're going to talk about aerobic and anaerobic metabolism. That takes longer. So we'll get ATP quick ways, slow ways, and we'll build this story up. We're going to talk first about one way of getting ATP. Then we'll add time frames, we'll add storage. As we go through, we'll start with the most basic story and keep adding to it and building on it. What we're actually going to be doing is we're going to take molecules that contain a lot of energy, and we're going to keep breaking them down into molecules that contain less energy. So we'll go stepwise through, a little less, little less, little less, as we take the energy out of the molecule, I guess is a way of saying it. So we'll take the energy out, do what we need to do with it, and keep getting molecules with less and less energy till we finally, like we said, get down to our carbon dioxide and water. We're also going to have stories about our fuels. Our fuels in general are going to be carbohydrates, fats, and proteins. We're going to talk about how much energy we get out of what. And if I said to you right now, what do you get more energy, or what is there more calories in? What contains more calories? A carb or a fat? You would probably very intuitively say a fat. I've yet to be asked, well, which carb, which fat? I'll just get instant answer, fat. And you're answering that from your everyday language. And actually, fats on average contain 9 kilocalories per gram, while carbs and proteins, and I think you're going to get this in nutrition, never hurts to do it twice, they contain 4 kilocalories per gram. So I would know this, and it's an average number. But what we're going to do is we're going to pick a carbohydrate, just happens to be glucose, the typical traditional place to start, and we're going to see how many ATP we get out of that. We're going to go through reactions, steps, processes, and ultimately get every ATP we can out of that. And then we're going to say, okay, well, we're going to pick a fatty acid. I don't know which one. We'll pick one when we get there. And we're going to see how many ATP we get out of that. And we'll compare it. And what we'll find is we're going to get a lot more ATP out of that fatty acid. And I'll say, remember when we first started talking about this? And when we're doing it in class, I'll bring you back to, remember I said, which do you get more calories from, a fat or a carb? And everybody said, intuitively, just said a fat. Here you go. Here's the number. And depending on which fat we pick, it's usually 3 times the ATP from that fatty acid than we had gotten out of the glucose at that point, probably about a month earlier. So we'll go and do that. Okay, let's talk about chemical reactions. If, at this point in the term, you guys went and talked to a trimester 2 student and said, how many reactions do you need to know for biochem? They'd probably say hundreds. Don't believe them. They need to know 6. And this is a little bit of a talk in off the ledge, before you get on the ledge speech. And then we'll do it as a talk in off the ledge once you get yourself out on the ledge, which Try 2 usually has by this point. So here's what I mean by that. We're going to do 6 different reactions. We're not doing thousands. We're doing 6. But we're doing those 6 different reactions to a lot of different molecules. So you can have 2 approaches. One approach, you can think of it as thousands of reactions and try to learn, well, we don't do thousands, but try to learn, tons of reactions. Or you can reel it in and saying, I'm doing this one reaction on all these different things, all these different molecules. That will systemize and organize you more, which, let's talk about the boards a little bit. If you want to go, and I think you probably got this in orientation, but just in case you didn't, if you want to go learn more about your boards, go to a site called nbce.org. And it's the National Board of Chiropractic Examiners. It will talk about all 4 parts of the national boards that you'll take. You'll take part 1 in trimester 5. There's 6 parts to that board exam. It's biochemistry, or the chemistry section, microbiology, anatomy, general anatomy and spinal anatomy, physiology. I'm forgetting one, I don't remember. But anyway, there's 6 different sections, and you're going to do those 6 different tests all in one morning or one afternoon. And the thing is, none of the questions are particularly difficult. The problem is 6 tests on 6 topics all at once. The other problem is 6 tests on 6 topics that you did a year ago. So I always use the analogy, it'd be kind of like you taking a test on the first 2 years of your undergrad right now. You know, you did well in it, you knew it, or you wouldn't be sitting in this class right now. But you've done lots of stuff since then and had lots of time to forget about it. That's the whole thing with part 1 of the boards. You're going to do other stuff in the meantime and have time to forget about it. So my point in telling you all this is 2 things. One is you need to really systemize yourself and you need to really organize yourself. So that's where we're going here. Systemize yourself into, rather than thousands of reactions, 6 reactions. And then organize yourself. As we go through our stuff that we're doing now, you know, a lot of these lectures are hitting an hour and a half. They take longer in class live because we have conversations. The PowerPoints are horribly long. When it comes board time, you're not going to have time for that. So we're going to do some things where we cut your notes down. You know, I'll say we have this PowerPoint that's 40 slides. Let's turn it into a couple pages. And we'll do a lot of that together because you need to cut volume down and organize you. You also need to systemize you. So anyway, with reactions, we're going to do 6 different types of reactions. Some reactions fall into more than one of these categories. So we're going to go through them one by one now, and then as we're using them, I'm going to say, okay, it's an oxidation reduction. Remember oxidation and reduction? And you might have to go back and say, well, no, but what is it? And it's just oxidation reduction again. Same reaction that you've done before again. Or we're making an isomer again. So I'll keep chasing you back to this in an attempt to get you to organize you. All right, so the first kind of reaction we're going to do is oxidation and reduction. And we're going to go through it. I know you did it in general chemistry and probably spent a decent amount of time on it, but just to make sure you remember it and get everybody on the same page, we're going to go back and do it. So here's what oxidation is. Oxidation is losing an electron. Here's what reduction is. Reduction is gaining an electron. But here's the thing with electrons. We can't take an electron off of something and just leave it there hanging out. We don't have electrons just hanging out waiting for us to put it onto something. If we take an electron off of something, it's going to go onto something, as in another molecule. If we take an electron off of a molecule, it's going to go on to another molecule. So oxidation and reduction reactions have to happen together. There's going to be other things that will take off a molecule and leave hanging out in a solution, and we'll talk about that. Or we're going to have stuff like, say, a water, we're going to assume it's hanging out in solution waiting for us, and we can put it onto a molecule or use it. So oxidation and reduction is not that case. They have to go together. We often call them redox reactions. Just kind of a cute word combining them. There's a couple of mnemonics to remember oxidation and reduction. I like oil rig. You also have Leo the lion says grr or something, and I don't remember that one. So oil rig, oxidation is losing, like most mnemonics, just the first letter. Reduction is gaining. And what we're gaining or losing, of course, is our electron. It's an electron. It's not letting me put the bottom of that E on. All right, so we're going to talk about that in a minute. We're going to gain and lose electrons. First thing, though, is oxidation state or oxidation number. Look at that as kind of a net worth. Let's say we have iron, ferric, ferrous, 2 plus, 3 plus. When we go back and forth between 2 plus or 3 plus, it's because we're gaining or losing an electron. So remember, an electron is a negative thing. It's kind of like a debt. Let's back up with this net worth thing. Let's say my net worth is whatever it's worth. Let's say, I don't know, I get really stupid for a minute and decide I need a brand new Lamborghini. So I'm going to go and take out a car loan and buy my brand new Lamborghini. So my net worth is whatever it is. I gain something, something being the debt that is my car loan. So I gained something, but since I gained that thing that's negative, that is my car loan, my net worth just decreased, even though I gained something. The something I gained was negative. So be a little careful with that. We think we're gaining something, something's increasing. But when I'm gaining something that's negative, my something is decreasing. So my net worth is decreasing. So if I'm a 3 plus and I gain an electron, I become a 2 plus. Or let's say the other way around. I have this Lamborghini car payment, whatever, this Lamborghini loan, and the bank lost all my paperwork. Well, what happened? Well, I just lost that negative thing. Since I just lost that thing that's negative, my net worth went up. I was at my 2 plus, lost my negative, minus a minus, I went to 3 plus. So my point in all this is just be a little careful. The thing we're gaining or losing is an electron, which is negative. So oxidation state increases when we get oxidized, decreases when we get reduced. We're gaining or losing a negative thing. The substance that I oxidize is the reducing agent because it's going to go and reduce something else. The substance that I reduce is the oxidizing agent because it's going to go and oxidize something else. Not super important. It just comes back to we can't oxidize without reducing. We're not going to reduce without oxidizing. Let's just draw this. All right, we're going to do a couple of reactions. We're just going to draw them. At this point, I don't expect you to know what any of these molecules are, but we're going to use them and talk about oxidation and reduction. You are going to know what they are later, and we'll talk about how you're going to use that. So let's do the second reaction first. I can have a molecule, let's say I have malate. Oops. It's an awful M. Try that again. I can have a molecule called malate, and I can oxidize that to a molecule called oxaloacetate. Here's the thing with electrons. Electrons travel with protons, and when I put an electron and a proton together, remember I get a hydrogen, an H. So, like a lot of things that we look at very, very mechanically, we're going to look at this very, very mechanically. We're going to do what's called chase the H's. So I'm going to oxidize malate to oxaloacetate. If you look at the previous slides, you can see I have more H's, chase the H's, on malate than oxaloacetate. I'm losing electrons there. For one molecule to lose something, another one has to gain them. So the molecule that's going to gain them is called nicotine adenine dinucleotide, NAD. Don't worry about it yet, we'll come to it. It's an electron carrier. So when it's in the form of NAD, it's an electron carrier not carrying any electrons. But I'm going to take the electrons off of malate, put them on NAD, which gives me NADH. So when we get rolling a little bit, what you're going to realize is the energy that was contained in malate is now on here, actually here, in the H part, in the electrons. That's going to go then and eventually give us ATP. So we're going to get kind of stoked about that. We've got an electron carrier, we'll call it, loaded up with electrons, and that's going to go and give us ATP. We'll also call it an ATP equivalent. And I'll start introducing that term a little bit now, even though it's not really important now. What it is like a check for ATP. So let's say, I'm a new patient in your office, and I'm grandma, and I still write checks. I'm still that annoying person that gets ahead of you in the checkout line at Publix, writing my check. And I wrote you a check for $30. So I gave you this physical thing that's worth $30. But it's not $30 that you can go and spend. You've got to do one more step with it. That's what an ATP equivalent is. You know how many ATP it's worth, how many ATP it's going to give you. Like, that check is worth $30. It's going to give you $30. Even though you don't have it yet, you got a couple more steps to do, or a step to do. You've got to go to the bank and cash it. That's NADH. I know how many ATP it's going to give me, but I don't have them yet. I got to do some steps to go and get those ATP, and we'll do that. So my point right now with it is, though, it's an electron carrier loaded up with electrons. It's an energy-containing molecule that can go and give me that ATP. So we said with oxidation and reduction that I can't do one without the other. So they're always going to go together. So this is my oxidation. Malate lost the electron. When it lost it, it became oxaloacetate. NAD gained it. When it gained it, it became NADH. So what you're going to start doing when we actually apply this and start doing stuff with it is a couple things. One is you're going to be looking at it like the what's in it for me. I'm going to say I oxidized something. You're going to say, oh, cool. What did I reduce? Well, I don't know if you'll say, oh, cool. But you'll say, what did I reduce? Meaning, I know if I took an electron off of something, it had to go on something. By it going on to something, I got a molecule that's going to go and make me ATP. So that's the what's in it for me part. You're also going to get very tuned into that reduction goes with oxidation, oxidation goes with reduction thing. But a couple things with that. There's a couple of different ways of writing it. I like this way because I get to see very distinctly, here's my oxidation, here's my reduction. But there's a downside to that. And let me get rid of all my mess for a second. There's a downside to that. When you look at a lot of the diagrams we're going to see and use and everything, it'll be written like this. And sometimes the NAD going to NADH will even be in a smaller font. So the arrow written like this looks very by the way. And in a way, it's the more important part of the whole thing. You know, malate went to oxaloacetate, that's important, but not necessarily giving us what we're focused on. If we're focused on the ATP, the NADH is what's giving us the ATP. So in that sense, it's kind of the important part. And it's written in this very by the way. And like I said, sometimes the font will even be smaller there. So you might not like that. You might want to say something like malate plus NAD goes to oxaloacetate, acetate, plus NADH. And totally up to you. Either one is absolutely correct. To me, I like the division. To me, it's clearer. You might say, hang on, this is as important. You know, why are we minimizing it? You might like this. They're equally correct. They're equally fine and totally up to you. One of the things we're going to do is we go through and do everything is you're going to do your notes by you for you. One of my goals in this is have you come out of these classes with a nice little packet of board notes by you for you. I'd like you to have a nice little 10 or 15 page package, and it's actually your project in all of this, of board notes by you for you. And usually when I say that, somebody will stick their hand out like, well, I bought a board review book. What do I need? Why do I need to do that? That by you for you is super important. I could give you my notes. I don't care if you want them, you can have them. But there's going to be questions that the question's not difficult, but figuring out what it's asking can be a little bit challenging. And I don't want you to miss a question because you didn't know what it was asking. So as we go through certain stuff, we're going to say, here's 3 different ways it could be asked. Put whatever you need in those notes to click your brain on picking up that's what it is. So that's the by you, for you part that's super important. Like I said, if you want mine, you can have them. But it's what makes my brain pick up on whatever. So it might not help you. So that's why a lot of times I'll say, you could write it this way, you could write it this way. That kind of thing, whatever sits right to you. All right, let's do the other reaction. We had succinate going to fumarate. I don't expect you to know what succinate or fumarate is yet. We'll get there. And while we did that, FAD went to FADH2. So what you can do to figure out what's going on, chase the H's. Here's the H. Did I gain it or lose it? I gained it. So this has to be my reduction. That means this, well, my writing's not working all of a sudden. This has to be my oxidation. So that has to be my oxidation. I could write it the other way around. Maybe I can write it the other way around. Fumarate might go to succinate. That to happen, FADH2 has to go to FAD. So what's going on here? Chase your H's. Here it is. I lost it. Oxidation is losing. then this has to be my reduction. When you go back to the previous 2 slides back, you'll see here, fumarate gained the H's that succinate, or that FADH2 lost. Okay, some vocabulary that we talked about. All right, next reaction we're going to do is chemical ligation. So we said you're going to start watching ATP. It's going to be like looking at price tags when you're shopping. You're going to be watching ATP. So what I mean by that is you're going to look at reactions that use or make ATP. So what a ligation is a reaction in which we use an ATP, and when I say use an ATP, we're absolutely using the energy. We may or may not use the phosphate. So we're going to use an ATP, break it into ADP plus a phosphate plus energy. We'll use the energy and we might use the phosphate. So in this case, we use the energy, but we just left the phosphate there. We can leave phosphates there, unlike electrons. Let's talk about that for a second. I want to clear up when I say leave phosphates there. When I say leave phosphates there, I mean within the scope of this class. So within the scope of the class, the certain molecules or ions that we're going to assume are there when we need them, we leave them there when we don't need them. And that's not really the reality. For example, like Dr. Krabbe will talk in nutrition about what you eat to make that phosphate be there available to us. We're going to leave carbon dioxide there, or we'll say we leave it there. Physiology is going to pick up on, well, you don't really leave it there. How do we get it in the bloodstream back to the lungs and exhale it if it's a waste product? How do we regulate water balance? Will be part of physiology. So you have your water sitting there because of physiology. Or you'll have your water, we'll leave it there, and physiology will talk about how to get it out of there. So even though we're saying we leave it there, it's there, it's kind of not. It's just really more a scope of the class kind of thing. Okay. So next thing we're going to talk about is isomers. So here's the thing with isomers. We're going to make a lot of them. What an isomer is another molecule that contains exactly the same components as the molecule we start with, but rearranged. So I might have, let's say, here's a good example. I might have C6H12O6, and that's glucose. Or I might have C6H12O6, and that's fructose. When I draw it that way, they look kind of awfully similar. They look kind of awfully similar because I'm just telling you what's in them. But what I'm not telling you in this is glucose is a 6-membered ring, fructose is a 5-membered ring. Glucose has 1 carbon sticking up out of the ring, fructose has 2 carbons sticking up out of the ring. Glucose is something you can process in every tissue in your body. Fructose is something you can process in your liver and your liver only. And there's a whole bunch of physiological implications of that. So when we write it this way, it's kind of not telling you a whole lot. So we'll get into that more. And my point when I'm saying this is I know how goofy it sounds, function follows structure, and sounds a little cliche, but kind of really does take the kind of out of there. So we're going to rearrange stuff a lot. We're going to take reactions or do reactions where we don't add or take away anything, but we just rearrange the molecule. Easy enough. But let me add something to that. When we rearrange the molecule, sometimes we're going to take a more stable molecule and rearrange it to a less stable molecule. You guys that have strong organic chemistry backgrounds sometimes don't like that. And you'll say, well, hang on here. I, I like my molecules stable. I spent a lot of time in organic chemistry making my molecules stable. I don't want unstable molecules. And you did, and I get it. But here's why we make our molecules unstable sometimes. Sometimes we have a reaction that we want to do, and we only have a certain amount of energy. It's like, I don't know, I have $5 in my pocket. I want to have lunch. Am I going to go to the Outback? No, I'm probably not even getting the funky onion for that. But I can rearrange my plans and go to Taco Bell and accomplish what I wanted to accomplish, I think. Can you still get lunch at Taco Bell for $5? Maybe not. But anyway, go with my example. So I rearranged to be able to do what I wanted to do on less dollars. Sometimes we're going to rearrange molecules to do what we want to do on less energy. And I know when I say it right now, usually, oh, okay. It's during a test that sometimes the organic chemist will start second guessing themselves on that. So it's something I'll say a few times just to make sure you remember it when you need to remember it. Okay, the next reaction we're going to do is group transfer reactions. We're going to move functional groups. Sometimes we're going to move it within the molecule. Sometimes we're going to move it from molecule to molecule. Within the molecule, we're making an isomer. Sometimes we'll move it from one to the other. Might be a phosphate, moving it from ATP onto a molecule. That's actually one of the first reactions we're going to do. Okay, next one we're going to do are hydra-something reactions, and let's talk about that. Hydra-something reactions are reactions with water. And there's two of them we're going to do. We're going to do hydration, and we're going to do hydrolysis. Hydrolysis. Lysis is splitting. So, with either one, we're going to start with the water, and we're going to split it up into an H and an OH, a hydrogen and a hydroxyl. And we're going to apply it to the other molecule. If we're doing a hydration, we're going to start with a molecule with a double bond. And I'm just making it up. And what we'll do is we're going to open up that double bond, leave the rest of the molecule. We'll put the hydrogen on one carbon, we'll put the hydroxyl on another. There's the hydrogen, and there's the hydroxyl. So that's my hydration. We can dehydrate, take the water off, put the double bond back. Sometimes we'll dehydrate. Yeah, we won't go there yet. Or we might do a hydrolysis. This time we've got a molecule, and I'm just making this up. I know it wouldn't actually work with this molecule. And we're going to split it. We'll split it. So what we'll do is we'll put, sorry, my writing's dragging. We'll put the hydrogen on one part, one half. I guess part, big half, little half. And we'll put the hydroxyl on the other part. So lysis is splitting, we actually split one molecule into two. So here's the hydrogen. Not going to let me draw my arrow. All right, so my hydrogen went on one half, my hydroxyl went on the other. For some reason, it's not letting me draw that arrow. Yeah, I guess I'm not drawing it. Okay, so the water-based reactions we're going to do are hydration and hydrolysis. That's it. Don't confuse it with hydrogenolysis, some reaction with hydrogen we're just not going to do, or hydra anything else. Okay, hydrolysis, properly said hydrolysis. I'm just trying to emphasize the lysis. We're cleaving, we're breaking the molecule we're applying the water to. So a hydrolytic reaction, one molecule is going to become two, split, lysis is splitting, split with water. We're going to add functional groups, and this one's going to have a little bit more variety to it. When we do that, that addition is going to be catalyzed by lyases. It's a category of enzymes that has multiple different enzymes in it. So we'll focus on them more as we get to the actual ones. What they're going to do is they're going to form a new double bond, or they're going to close something up and form a ring structure. So we're starting with just one substrate to go in one direction, or two to go in the opposite direction. But we'll focus on it more when we get there. There's some of our decarboxylases, aldolases, things like that. Sometimes they're a synthase. So a couple of examples, and like I said, we'll focus on it more when we get there. Here's the point of the whole thing right now. When we look at this slide, it looks like a big mess. And it's processes we're going to do. We're going to do the citric acid cycle. We're going to break down fatty acids. We're going to make fatty acids. We're going to break down amino acids. We're going to make amino acids. And when I look at that, it looks like I have 4 different big, messy things with a whole bunch of reactions going on here. Here's the thing, though. I have 2 reactions on this whole page. I'm either hydrating, dehydrating, water in, water out, and I'm oxidizing, reducing. That's it. So when you look at this, first it looks like a mess and a lot to know. But when I say to you, there's 2 reactions here, that reels you in a little bit, like, oh, which 2? Where are they? So it organizes you. And we'll do that when we do each one of these processes, so that rather than learning a million random things that you kind of already learned, you're just going to apply what you already learned to a new molecule for a new process. Much, much easier that way. So again, a little bit of the talking you off the ledge before you're on the ledge, but I want to lay out the approach and have you do that approach to make it easier as you do it, not create a bunch of randomness, then have to go back and do it. Okay, so we're going to stop here, and the next place we're going to go is proteins. So we'll start with a new video and a new module with that. So you have a quiz to do now. Go ahead and do that, and then we'll move on to the next module.